Hi class, welcome back to Computational Tools. For our third tutorial today, we're going to be writing our own function files and executing them in MATLAB. So of course, as usual, let us just start by saving our tutorial. I'm just going to save it with my name. This is tutorial number 3. Now, we have been saving our tutorials as script files, so those .m script files, which saves a series of commands that can be executed at a later date. So if you went through and you opened up one of your previous script files, one of your previous tutorials and ran it, it would run as it ran while you were working on it. So it saves that, which is important because if you type directly into the command window, you cannot save what has been in the command window. Now, MATLAB also recognizes function files. These are M files like script files that start with the word function. So the first word on the first line in a function file is going to be function, and then MATLAB recognizes that you are writing a function, that script is actually a function. So in contrast to script files, they can accept input arguments and return outputs. Hence, they are analogous to user-defined functions in programming languages such as Fortran, Visual Basic, or C. The syntax for the function file can be represented generally as first you have your function, so this is telling MATLAB that your script is a function. Then you set your output variable equal to the function name, which is the name of your file, and then your list of input arguments. And below that, you'll have comments that are going to be your help comments. So you can see that my comments here, these percent symbols, are just so that I can write in these comments, and when you execute these lines, MATLAB will not do anything with them because they're comments. But in a function file in a script file that you're saving as a function, it's helpful to include comments underneath defining what the function does so you can recognize it at a later date, what your input variables are, what the units are for your input variables, what your output is, what the unit is for your outputs, and any given assumptions in the function if it's a model. And then there's going to be the statements. So force equals m times a, for example, mass times acceleration. So that would be an example of a statement. And then the value you're assigning to your output variable. And we're going to practice this today in this tutorial. And so what we're going to do is we're going to go through and we are going to write a function for that velocity statement, the terminal velocity of a bungee jumper that we were looking at last tutorial. And one thing to notice is that with these help comments, the first line of the help comment is called the H1 line, and that line is searchable. And so if you can't remember exactly what you called your function, it's really useful in that H1 line to use some descriptive terms that you can then search and find your function once again in your help catalog in MATLAB. So once again, looking at our bungee jumper, we are going to generate an M script that is going to be a function in MATLAB, a MATLAB function. So what we're going to do is let's open a new M file. So not a live script. It's not a live script. It's not going to be a .mlx. It's going to be a .m file. So I just hit a little plus there to open a new one. You could have done new script or command N if you have a Mac. And so what I'm going to do is now I'm going to go back to the third tutorial, and I am going to copy and paste lines 48 through 59 of code into that new untitled function. So I'm going to hit Command C, or if you're on a PC, Control C, or just right click, copy, and then I'm going to hit Command V or Control V. I'm going to paste it into my new script. So there are a couple things I'm going to have to remove here. So I have these comments on the left just because I did not want MATLAB to run them in my other script. So what I'm going to do is up here in our editor tab at the top, you can see there's comments, and you can delete an entire column of comments with this uncomment. So I'm going to highlight my whole function code, and I'm going to uncomment. Okay, and then the last thing is I added single quotes in here, so let's get rid of those. Okay, and so now you can see that MATLAB is recognizing this as a function. Our output is going to be velocity. Our function is going to be called freefall, and our input variables are going to be time, mass, and drag coefficient. And so on my H1 line, I have freefall, and this gives us the bungee velocity with second order drag. That's what this function's doing. And then the line below that says what we're doing. We're computing the free fall velocity of an object with second order drag. We have our inputs listed. So these are all comments, once again, just describing what is going on in the function, where T is time in seconds, mass is mass, and M is mass in kilograms, and CD is second order drag coefficient in kilograms per meter. And our output is going to be V, the downward velocity in meters per second. Okay, then we have our statement. Then we have, so in this case, what we have is we're saying, okay, well, one variable we're going to define in the code. It's not going to be something that we have to input. It's going to be predefined, and that's going to be G is equal to 9.81 meters per second squared, which is the acceleration due to gravity. So then below that, we have our statement line where our output V is equal to the square root of G times M over CD times the hyperbolic tan of the square root of G times CD over M times T, the same equation statement we have been using for the bungee velocity. So now if I hit run, MATLAB is going to want to save it in our current folder in our working directory. And you notice that it wants to save it with the name freefall because it recognizes that that is in fact the name of your function. So let's save that in our working directory under the name freefall. And you also notice that it is, the format is just a .m regular MATLAB code file. So save. Now it has taken on the title freefall. And let's go back to our tutorial. So now let us try, we can call this function now. So because this function, freefall, you see how it has that little f sub x in your current folder right there? So this function freefall is living in your working directory, and because you're in that directory, you can call it in the tutorial script that you have open. So let's try to call freefall. So freefall, and remember we have to have 3 inputs, and we get this little help, these suggestions with MATLAB and saying, okay, well, the first input is going to be T, the second one is M, and the third is going to be CD. So for time, let's do 12 seconds. For M, let's do 68.1 kilograms. And for drag coefficient, let's do 0.25. Okay, and so if we run this, we get our output. Velocity is 50.6175 meters per second. Pretty cool, huh? So one advantage of a function M file is that it can be invoked repeatedly for different argument values. Suppose that you wanted to compute the velocity of a 100 kilogram jumper after 8 seconds. So let's do that. And I'm just going to copy and paste here. Okay, and so you see that our output is going to be 53.1878. So if we go back in our command window, we can see that for 68.1 kilograms, after 12 seconds, we had 50.6175. And for 100 kilograms, of course, the velocity is going to be greater, but this is only after 8 seconds. And it also, the command window is showing you that the value for G used in this function is 9.81. And if you wanted to suppress that G, what you could do is you could go back to your function script And after g equals 9.81, you could just put a semicolon there. And so that would not, so that way it would not show up in your command window, and the only output you'll see is the answer. So let us just run this. Okay. And so then if we rerun this line, you see that there's no more G that's coming out in your command window because we suppressed it in our function file. So one advantage, so to invoke the help comments, let's type help freefall to learn a little more about it. And you can see the comments that you included in your function file are what comes up in the help documentation. If at a later date you forgot the name of this function but remembered that it involved a bungee jumper, you could enter look for bungee. And MATLAB would recommend, okay, well, the function freefall had in its H1 line, bungee velocity was second order drag. And so that's another way you can look up documentation, or if you couldn't remember what you called a function, you can search by keyword by using the look for command in MATLAB. Now, what happens if we type G? Okay, so you notice in your workspace, the only thing kicking around in your workspace is the answer from the most recent run of your free fall function with the 100 kilogram jumper. There's nothing else in your workspace. G, the acceleration due to gravity, lives in the function free fall, but it does not live in your workspace. So if you just type it, if you just type G in this script here, nothing is going to happen. It's not going to recognize it. So you get that it's an undefined function or variable. So go ahead, comment that out in what happened, explain what happened, and I'm going to comment out this G here because what's going to happen is anytime I run a line, it runs the whole tutorial script, and so we'll keep getting that error that G is undefined. So function variables can return more than one result. In such cases, the variables containing the results are comma delimited and enclosed in brackets. For example, the following function, stats.m, computes the mean and the standard deviation of a vector. And we're going to type this function into a new script named stats.m, and then we're going to run it. So when you upload this tutorial to Moodle, I also want you to upload your function files with that tutorial because I open those with your tutorial and make sure that it's going to call the functions properly. So that's part of what you submit here now. So I'm going to open up a new script and I am going to copy and paste the stats function into the new script. We're going to delete these single quotes and we are going to delete the first column of comments. And when we run it, you notice that it's named stats by default. And then we have no descriptors here, but we have that our output is going to be the mean and standard deviation. N is going to be the length of x. And so we're going to compute the mean, which is going to be the sum of x divided by the length of it. And then the standard deviation is going to be the square root of the sum of the difference between the x and the mean squared divided by n minus 1. And whenever you are raising, when you want to raise each element of a vector to a power or multiply or divide, what you need is this dot before the operator, or else it will not work properly. Okay, so now let's try to apply the stats function. And so we're going to have y equal to the vector 8, 5, 10, 12, 6, 7.5, 4. Okay. And what we want is ms is going to be equal to stats y. So what we're saying here is we're defining a vector with m and s in it, and whatever our output for stats y is are going to become that vector. Okay, so what we get is m is 7.5 and s is 2.8137. So what you can see is that our output is going to be m and s, and those are reported. MATLAB variables have a property known as scope that refers to the context of the computing environment in which the variable has a unique identity and value. Typically, a variable's scope is limited either to the MATLAB workspace, so over to the right here, or within a function, as we saw with the acceleration due to gravity in our freefall function. This principle prevents errors when a programmer unintentionally gives the same name to variables in different contexts. So say you had G in your workspace defined as something else, but then you ran the freefall function. What's going to happen is within the freefall function, that G is still going to be as it was defined within the freefall function. It will not be overridden by the G in your workspace. But if you call G directly in your script, it's going to use the G from your workspace. So that enables you to use the variables in different contexts. Any variables defined through the command line are within the MATLAB workspace, and you can readily inspect a workspace variable's values by entering its name at the command line. And so when you enter G at the command in the command window or in a script, as currently, it's going to be undefined because we don't have G defined in our workspace. However, workspace variables are not directly accessible to functions, but rather are passed to functions via their arguments. For example, let's create a function that adds two numbers, and we're going to name it adder. So we're going to create another function. So we're going to copy this function. We're going to open a new script. We're going to paste it, and we're going to delete all my comment stuff, the single quotes, the column of comments, and this is an adder function. It's going to add A and B, and our output is going to be C. Okay, so we're going to run this, and we're going to go back. Now let's type x equals 1, y equals 4, and c equals 8. So we're going to save this to our workspace over here. So you can see now we have C, X, and Y saved to our workspace, and the only one that showed up in our command window was C equal to 8 because we did not suppress that with a semicolon. So as expected, the value of C in the workspace is 8. So now we're going to type D equals adder. So we're going to run the function adder, and we're going to add X and Y. So it should be 1 plus 4. Okay, so you notice D is equal to 5, right? 1 plus 4 is 5. So now let's type C, X, and A and see what happens. Okay, so we got an error. So A is not defined in our workspace. However, A is defined in adder. Right? A is going to be one of our input, and in this case, our input was X. However, if you look at X, we have saved it as 1 in our workspace, and X is equal to 88 in our function. So the X that it called, that the function adder called, was from our workspace because that was an input. It did not call what X was defined as in adder, right? Because X is not defined as an input of adder. If we put C equals adder X comma B, and then the x used would be x equals 88, but that's not the case here. So describe what happened, and I'm going to comment this line out as well so that it doesn't mess up the code as we proceed. So as we have just illustrated, the function's argument list is like a window through which information is selectively passed between the workspace and a function or between two functions. Sometimes, however, it might be convenient to have access to a variable in several contexts without passing it as an argument. In some cases, this can be accomplished by defining the variable as global. This is done with the global command, which is defined as global xyz, where x, y, and z are global in scope. If several functions, and possibly the workspace, all declare a particular name as global, then they all share a single value of that variable. Any change to that variable in any function is then made to all the other functions that declare it global. Stylistically, MATLAB recommends that global variables use all capital letters. Of course, this is not required, it's just recommended syntax. So we're going to try an example using the Stefan-Boltzmann law. And the Stefan-Boltzmann equation is used to compute the radiation flux from a black body. Now, a black body is an object that perfectly absorbs and re-emits all incident radiation, whereas a white body perfectly reflects all incident radiation. So the equation is going to be given by J is equal to sigma times T to the fourth, where J is the radiation flux in watts per meter squared, and sigma is the Stefan-Boltzmann constant, which is my favorite constant because it's actually really easy to remember because it's 5.67 times 10 to the minus 8, 5678, and the units are watts per square meter per Kelvin to the fourth. Now, Kelvin is an absolute temperature. The symbol for it is K. It does not require any little degree symbol before it. It's just K. And absolute temperature means that it's defined such that 0 Kelvin is absolute zero, and that is the point at which, that is the temperature at which all molecular motion ceases. So that means it's absolute. There's nothing colder than 0 Kelvin. And 1 increment in Kelvin is equal to a degree in Celsius. And the difference between Kelvin and Celsius is that 0 Kelvin is equal to negative 273.15 degrees Celsius. So in accessing the impact, so what we're going to do is we're going to go through an example. And that example, we are going to assess the impact of climate change on water temperature. And we're going to use the Stefan-Boltzmann law, the Stefan-Boltzmann equation, to compute the radiation in terms of a water body's heat balance. For example, the long wave radiation from the atmosphere to the water body is given by this G sub AM from the atmosphere to the water body. So this is the long wave, and this is going to be calculated as follows. We're going to have an emissivity. So an emissivity of 1 would be for a perfect black body. This emissivity is going to be 0.97 times sigma times the temperature of air. So this is going to be the temperature of air in degrees Celsius. That's why we're adding 273.15 to it to convert it to Kelvin. And then we're going to raise it to the power of 4. And then we are going to multiply that times another factor in which we're seeing how the radiation is exchanged between the water and the atmosphere. And so that's dependent on the emissivity of the air. So the temperature of the air is the temperature of the air above the water body in degrees Celsius, and E air is the vapor pressure of the air above the water body. So, sorry, this is the vapor pressure, and that's going to be in millimeters mercury. So the water the vapor pressure of the air is going to be 4.59 times E. Okay, so this exponential function is the same thing as raising e to the power of everything in the parentheses. So it's going to be 17.27 times TD, which is the dew point temperature for the air in degrees Celsius, divided by the conversion then, divided by, 237.3 plus TD, which is just going to be a conversion factor in there. So the radiation from the water surface back to the atmosphere, so the back radiation, JBR, is going to be calculated by 0.97, the emissivity, times sigma, times TW plus 273.15, so that's just converting Celsius to Kelvin raised to the fourth, where TW in this case is the water temperature now in degrees Celsius. We will write a script that utilizes two functions to compute the net long wave radiation. In other words, the difference between the atmospheric radiation in and the water back radiation out for a cold lake with a surface temperature of TW is equal to 15 degrees Celsius. On a hot, T air equals 30 degrees Celsius, and humid, the dew point is 27.7 degrees Celsius summer day. We will use global to share the Stefan-Boltzmann constant between the script and the function. So we are going to type, I'm just going to copy and paste, CLC, and CLC is just clear command line, the command window, so that's clearing out your command window. We're going to use a compact format, and we're going to define sigma as a global parameter, and that is going to be 5.67 times 10 to the minus 8, so we use e to the minus 8. Temperature of air is 30, temperature of water is 15, and dew point is 27.7. So you can see our sigma shows up in all caps in our workspace. So now let's go and we're going to create two more functions. We're going to create an atmospheric long wave radiation function and a water back radiation function. So we're going to create these in two different scripts. So let's copy and paste the first one into a new script, and let's delete my quotes, and let's delete the comment. Okay, so this is going to be our atmospheric long wave radiation. It's going to use our global sigma, and then we have our vapor pressure equation in here and our radiation equation and end. So our inputs are going to just be T air, the temperature of the air, and the dew point temperature. So we'll run that, and we're going to save it in our working directory as atmospheric longwave.m. Okay, so you can see that's there. And then we're going to create another new script, and we're going to go back to our, I'm just going to delete these other tabs because they're getting in my way. And we're going to create our water back radiation function. So I'm going to copy and paste that into a new script. Okay, I'm going to delete the single quotes. Delete this column of comments, and I'm going to run it. Okay, so that's water back radiation. Save it. Okay, so now we have those two functions, and you can see that's also calling the global sigma. Okay, so now we're going to enter JAN is going to equal atmospheric long wave rad. So that's calling our function. Just note you have to type it exactly how it's typed in the title of your function, or else MATLAB won't recognize it. And we're going to have T air, comma TD. And the reason I could write them just like that, those input parameters, is because they're already recognized as specific values in my workspace. JBR is going to be equal to water back rad, and we're going to use temperature of the water, which is also already defined in my workspace, so that is fine. And then we're going to define our net long wave radiation. It's going to be the difference between JAN, So the radiation from the atmosphere to the water and the back radiation from the water, JBR. So the difference between the two. Okay, so you can see it called upon our sigma just fine, our Stefan-Boltzmann constant. And our outputs then are JAN is going to be 354.8254 watts per meter squared. JBR is going to be 379.1659 watts per meter squared. And so the net is going to be the difference between the two, which is going to be 354.8254 minus 379.1659, which gives us minus 24.3405 watts per square meter. So for this case, because the back radiation is larger than the incoming radiation, the lake loses heat at a rate of 24.34 watts per square meter due to the two long-wave radiation fluxes. If you require additional information about global variables, you can always type help global. The help facility can also be invoked to learn about other MATLAB commands dealing with scopes such as persistence. So go ahead, pause this if you need to, and explore these different help commands and look for help global. Functions can call other functions as well. So although such functions can exist as separate M files, they may also be contained in a single M file. So for example, the M file in the free fall example without comments could have been split into two functions and saved as a single M file. So you could have done function V is equal to free fall subfunction, where V is equal to velocity, where T, M, and CD are the inputs. And then you could have called upon another function where you type in the statement there. So you go ahead, give that a try, and save it. So create an M file for the free fall subfunction, and try this last run the subfunction, and save all your code as a script. Upload all your supplementary function files with this tutorial, and that is all for tutorial number 3 for MATLAB, and I will see you next time for tutorial number 4.